Okay, let's take a look at our problem here. Okay, so we've got a ball thrown into the air, initial velocity of 90 feet per second. We have a function for the distance in terms of time. It's 90 times t minus 16t squared. And we're going to find the average velocity for the time periods beginning when t equals 1, lasting these durations. Okay, so the first average velocity will be from 1 to 1.5, and then B from 1 to 1.1, C from 1 to 1.01. And this is a nice illustration of the relationships between average velocity, instantaneous velocity, the gradient of the tangent, and how that can be used as an estimate for the instantaneous velocity, and all this good stuff, sort of the first days of calculus, I guess. Let's look at our function. Good to draw these things. So it's a curve, right? It's a parabola, the t squared. And we want to see how this purple line, how the gradient of that changes as the dt changes. Okay. So we're going to look at some specific dt's. So the first one is when dt is 0.5. Right here it's 1. So we're going to go from 1 to 0.5. Okay, so notice that the gradient of the purple line is increasing. The gradient is dy over dt. And so we're going to calculate the average speed by calculating the change in the distance over the change in the time. And so we can get the distance from the function, and we should match the dy dt. Okay, so we've got that calculation, and so you go through that and match that to 50. Okay, dt is getting smaller now, down to 0.1. You notice that the gradient is increasing. And there it is, there's the gradient. Again, we calculate the average speed by putting the numbers into the function. And so it's from 1.1 to 1. You should match the gradient of the purple line, which is 56.4. Okay. Now dt is getting so small that it's going to vanish here to 0.01. And you should notice that this is close to tangent to the curve, right? The difference is so small. Same process, calculate the distance over change in distance over change in time. Should match the gradient, which is dy over dt. Okay, so this should give you a sense now that we are approaching the instantaneous velocity at t equals 1 as dt gets smaller and smaller. So finally, we're asked to give an estimate of the instantaneous velocity at t equals 1. So it's at this point. And a reasonable estimate would be 58, seems to me, because as dt gets smaller, we can see that the gradient of the purple line is increasing. So it's going to be slightly more, but not too much more than 57.84. So 58 is a good guess. And if you know anything about the derivative, you can take the derivative and calculate the value at t equals 1, and you see that you do get exactly 58. And so not only is it a good estimate, it's exactly correct, exactly the correct answer. So, okay, I hope this is helpful. I think it gives a good illustration of, again, the relationship between average speed and the delta t, the change in t. As that delta t gets smaller and smaller, the average speed approaches the instantaneous speed. Okay.